Hi there, for a change not a multimeter but an infrared thermometer provided by Erickhill for review. I did not pay for it, so I marked this as a promotion, but for my previous reviews you know that this doesn't stop me from sharing all my findings with you. In the box is a nice holster containing the thermometer and a pair of AAA batteries and a manual. The manual contains 6 languages and is well written, containing all the important aspects of using the thermometer, including the distance to spot ratio of 12:1 and a short table of emissivity values. More about this later. The specs are here. My unit is the ROOK 600, which measures up to 600 degrees. Nice. The accuracy is ±3 degrees for negative values and ±1.5 degrees for 0 to 100 degrees Celsius. For higher values, it is ±1.5% of the reading. That means the error increases with temperature. If you read 200 degrees, for example, the real temperature could be 3 degrees higher or lower. For 400 degrees, it's ±6 degrees, and so on. To make my review of an infrared thermometer vaguely more interesting, I decided to compare the ROOK 600 with my trusty Uni-T UT300S, which I had for many years. As you can see, the UT300S only goes to 400 degrees, but in truth I never got even close to that temperature. With ±2 degrees Celsius or 2%, the UT300S is slightly less accurate than the ROOK. At 200 degrees Celsius, for example, the UT300S could be ±4 degrees off compared to only ±3 degrees for the ROOK. It is interesting that the UT300S has a repeatability statement. This means in addition to the error caused by the basic accuracy statement we just looked at, there's an additional uncertainty of ½ degree Celsius or ±0.5% when repeating the same measurement. The ROOK manual doesn't state this. In practice, at least in the room temperature range, if the meter is held steady and the target temperature is constant, I found little or no change from repeated measurements for both meters. The only real difference seems to be that the ROOK measures infrared from 5 micrometers, which is the mid-infrared band, to the long infrared band, while the UT300S limits itself to just the long infrared band. The ROOK shows the type and temperature range on one side, and a diagram explaining the distance to spot size of 12:1 on the other. I find that this is somewhat better explained in the diagram on the UT300S, which has the same 12:1 ratio and some standards it complies with on the other side. The business end of both in comparison. The UT300S is a lot smaller. Most noticeable is that its laser is above the IR lens, while in the ROOK it's below. The two rear LCD screens are identical in size. The ROOK's temperature display is larger and easier to read, while the UT300S temperature digits are quite a bit smaller, but on the other hand, the display always shows the current emissivity value of 0.9 in this case. I like that. The ROOK only shows its emissivity setting when changing it. The menu in the ROOK is selected using the mode key. At every key press, it cycles through max for maximum temperature, min for minimum temperature, AT for ambient temperature, EMS for emissivity, cal to allow calibration, high for high temperature alert threshold, low for low temperature alert threshold, and back to the main display. In the main display, the CF button toggles between Celsius and Fahrenheit. In the other modes, this increases a value. Similar, in the main display, the right button turns the laser or the backlight on/off, and in other modes it decreases a value. I am not going through all these options, they are pretty self-explanatory, but just briefly the cal menu I had not seen before. It allows you to calibrate the 0 degree offset. The manual doesn't really elaborate on this, but I think if you measure an object at known 0 degrees and the meter doesn't show 0, you can use the cal to enter an offset to correct this. Lacking a large enough object at exactly 0 degrees, I have not tried that out. Here's how to change or even just check what the emissivity setting is on the ROOK. I have to hit the mode key 4 times to see EMS and then use the left or right button to change the value. To exit, I have to press the mode key another 3 times. Pretty clunky, especially if you pressed mode one time too many and have to keep going around all menu items again. The UT300S has, in my opinion, a better implementation. First of all, you see the current emissivity all the time. To change, press the set key and emissivity is the first item. Just hit the up-down keys to change. A long press of set gets you back out of settings without having to go through any of the others. You may wonder why I pay so much attention to the emissivity setting. The reason is that you need to get the emissivity setting correct or your measurements will be completely wrong. Emissivity is defined as how good a material is in emitting energy as thermal radiation. It is expressed as a ratio compared to the emissivity of a perfect black body, which has the highest possible emissivity of 1. For two materials at the same temperature, the one with a higher emissivity will radiate more energy. To convert the amount of thermal radiation the Ir-Thermometer sees into a temperature, it needs to know the emissivity of the material. If you set a low emissivity, you get a too high temperature reading and vice versa. There are tables on emissivity. Here are just 2, one from the manual and the other from Wikipedia. There are more tables with far more entries on the web. The problem is that these tables rarely agree. Here we have just one aluminium with 0.3, while the Wikipedia entry has 4 different aluminiums with emissivities between 0.03 and 0.9. The general observation is that better tables provide more specific materials which hopefully resemble the material you are trying to measure. As far as the table in the manual is concerned, it's way too simple to be of much practical use. The other problem is with very shiny objects, such as this 5 mm thick aluminium plate at 21.4 degrees Celsius. I'm using the UT300S for this because you can see the emissivity setting, but the Rook behaves exactly the same way. It is possible to get a readout that is roughly the correct one, but mostly the temperature is way higher. This is because the plate mirrors the thermal radiation from the ceiling light and my hand holding the meter and so on. Because of the low emissivity for shiny aluminium, those mirrored temperatures are way higher than they are in reality, but in any case make measuring the real temperature of the aluminium plate almost impossible. To test the thermometers, I therefore coated the aluminium plate with black high temperature paint. Its temperature measured by the thermocouple is 27 degrees Celsius. The UT300 is reasonably close given the uncertainty of choosing the right emissivity. And so is the Rook, using of course the same emissivity. The temperature of the plate is now close to 51 degrees Celsius. The UT300 is reading close, and the same for the Rook. And a plate temperature close to 94 degrees Celsius. With 98 degrees Celsius, the UT300 is reading about 4% too high. And so is the Rook. At nearly 143 degrees Celsius, the UT300 reads 151.8 or 6% high. The Rook is better with 146.9, just 2.7% high. At 194 degrees Celsius, the UT300 is reading 204.8 degrees Celsius or 5.5% high. The Rook is slightly better with 202 degrees Celsius or 4% high, but dropped the decimal point from the readout. At nearly 249 degrees Celsius, the UT300 is nearly 7% off, but still showing 4 digits. The Rook is using 3 digits and it's only 4.4% off. I had to stop there because at 300 degrees Celsius the paint covering the plate started to give off lots of fumes, despite the sales blurb on the can promising it being good for 600 degrees Celsius. The results graphically. The Rook 600 seems to deviate less overall, but there's likely a common cause for the high error both thermometers show. The most likely cause is that despite using a 5 mm thick aluminium plate, there might be a temperature gradient from the edge where the thermocouple measured to the center where I was aiming with the infrared thermometer. So rather than absolute accuracy, the best these measurements can confirm is that both meters behave the same, and that measuring temperature accurately using infrared thermometers is definitely not easy. Another interesting fact is that from 200 degrees Celsius the Rook sensibly switched to just show full degrees, while the UT300S kept going with 4 digits, showing tenths of degrees, where the accuracy specs really do not warrant a readout of that precision. The other thing I wanted to test is how accurate the laser aim point is. For this I mounted this 47 ohm resistor on a cardboard target. Running 10 volts through it at a current of 230 milliamps means the resistor has to dissipate slightly more than 2 watts and it will get very hot. I measured at about 80 degrees with a thermocouple. At 1 meter distance I'm using a scan function to find the hottest point, not worrying about the actual temperature. Sadly the camera can't focus on both the thermometer and the laser, so you have to trust me to remember where the hot spot was and reproduce it with the thermometer out of view. The UT300 laser seems to aim about 3 cm above the target, while the Rook about the same distance below. That one is above and the other below the target is not a surprise if you recall the way the two lasers are arranged on the thermometers. The laser is really only useful at longer ranges. In both meters you can turn the laser off. For example, this is how you turn the laser off in the Rook, and it remembers that setting. A long press turns the backlight off, but sadly the backlight off is not remembered and lasts only until the Rook turns itself off. When it restarts, the backlight is by default back on. Let's see what difference that laser and backlight have on battery consumption. At power off, the Rook is in fact not really off, but still draws 1.2 microamps. Doing a measurement with laser and backlight draws slightly above 15 milliamps, and just displaying the result is about 5.2 milliamps. Doing a measurement with a laser but no backlight is 12.2 milliamps, and displaying the result 1.1 milliamp. Turning the laser off but with backlight is about 5.3 milliamps. I tested how soon the low battery indicator comes on by gradually lowering its supply voltage you can read on the multimeter behind the Rook. 2.55 volts, which is quite early for a nominal 3 volt supply. I did the same measurements for the UT300S and the results are in this table. In both cases the thermometers draw current when they are off. It is not a lot, but it's something you should be aware of because it may promote battery leakage if you do not use them for long periods. The laser pointer costs a lot of current, so it's best to keep it off until you really need it. In particular for the UT300S, keeping the backlight off really saves a lot of energy. That would also be the case for the Rook, but as you have seen, it does not remember that setting. Overall, the Rook has a slight edge because running from 2 sets of AAAs is far more economical than the 9 volt battery of the UT300S. The problem is that the low battery indicator threshold is right in the normal voltage range for 2 rechargeable batteries. You can use rechargeable batteries in the Rook, but the low bat symbol will come on a lot sooner than you might expect. The economics of the UT300S with its 9 volt batteries would normally lose out against the Rook's AAA battery, but the low bat on the 300S comes only on when the voltage drops below 5 volts, which means it really uses that battery until there's nothing left. The low threshold makes it very suitable for rechargeable 9 volt batteries. And speaking of battery, changing or replacing the Rook's batteries is a breeze, requiring no tools and can be done in seconds. Perfect if you only use it occasionally and want to avoid damage by leaking batteries. While the UT300S has the same mechanism, it's a bit more fiddly to unclip and replace a 9 volt battery. The Rook 600 SP has a lot of plus points. The use of inexpensive AAA batteries, the large measurement range with decent accuracy specs, and an easy to read temperature display. It also comes with a holster for wearing it on a job if that's needed. My only criticism on the Rook is that checking the emissivity setting requires too many button presses. This clunky process is annoying if you can't remember what the last setting was or someone else may have used the meter earlier. The best solution is surely displaying it all the time, but maybe it's possible to at least show it briefly during startup. Besides this, the ROOK 600 is a competent infrared thermometer, and I would like to thank Erickhill for sending it in. If you like my videos, don't forget to subscribe if you have not already, and maybe consider becoming a Patreon. That would really help this channel. The link is in the description. As a Patreon, you always get early access to videos, a blog and other exclusive content. Thanks for watching.